recording. Here we go. Okay, next. We have y something like this. So in order to derivate it, I'm going to rewrite it as 1 plus cosine of x in power 1/2. Because this way, you see that we have composition of functions. One function is 1 plus cosine of x, and the other one is taking the square root. So this will be 1/2 then of x times the derivative of what is inside. And derivative of what is inside is minus sine of x. So I'm going to rearrange this a little bit. This will be minus sine of x over 2 square root 1 plus cosine of x. The idea here is not to get impressed by all the mathematical paraphernalia and think of the functions as functions. And in this way, in this sense, derivative has very simple rules: chain rule, composition rule, and linearity. And that's it. You apply them to the letter, step by step, and you will always get to a solution. So the slope of this curve in any point will be given by this. Nice. Moving on. Ooh. Now, we observe two things here. The first one, we have a product of trigonometric functions. The second one, the variable is not x, it's t. What do we do if the variable is not x, it's t? We just operate with it. Okay, most of the applications of this kind of tools are generally related to time, which is where the t comes from. So let's see how this works. So we have the product of the functions, that's the derivative of the first times the second underivated, and you know how the rest goes. The derivative of this is minus a sine at times sine at plus this is derivative, sorry, this is underivated plus the derivative of this. This is cosine of at, and this is a cosine of at. What do we have here? Here we have sine squared of at, cosine squared of at. So this is a multiplying cosine squared of at minus sine squared of at which is equal to a cosine of twice AT. This is the formula for the cosine of the double angle. Now, please don't forget this and this. This is not free. This is the derivative of AT. And this is not free. This is the derivative of AT because this is a composition of functions in the end. Now, questions? If I rewrite this function to cosine AT plus 1, we would do the exact same. Let's do it. Actually, I'm going to give it another twist. So we don't get bored. In this case, we have derivative of the first. This will be minus the sine of AT squared plus t times the derivative of what is inside. And the derivative of what is inside is 2AT plus 1. Yeah. Plus, because this is the derivative of a product. Now, this goes without derivative. And here, the derivative of this composition of functions, the derivative of sine is cosine. And the derivative of what is inside, it's a plus 2t. And I don't see how we can simplify this, so this is probably the end of it. In the end, you always have to remember that rule. The only thing is, if you have to implement both at the same time, you have to implement both at the same time. So in this case, we have the product of two compositional functions. So we apply the rule for the derivative of product, and then inside we have the derivative of a compositional function. So we unravel it. This can get tricky sometimes, especially if you're not familiar with this type of manipulations. So I suggest you do as many of these as you can, really, because that's what will allow you to recognize this type of situations. But you have two rules: composition and product. Now, we're going to see an application of derivatives on limit solving. Now, this limit looks terrible. It looks absolutely awful. So what can we do with it? This is 0 over 0. So we can apply. I don't know if you have seen it here in the lecture of today. No, I don't see it here. Good. All right, give me a second to figure out how to solve this without that rule, because that's like literally the first thing that comes to mind, right? You apply this guy's rule. Don't tell us, Jeff. Okay, this is what we are going to do. So if we have a quotient of two functions that tend to either infinity or 0, then yeah. All right. Beautiful, isn't it? What we have here, limit on x, limit on x, limit on x, is that the quotient, the limit of the quotient of functions is equal to the limit of the quotient of derivatives. So let's apply it. But before we do that, let's put it here. You know, before we play with the toys, let's be good children. And you're going to tell me if you like this other solution. This is the limit when x tends to 0 of sine of 2x divided, sorry. This thing goes like this. And now what I'm going to do is take the cosine out of the equation. This looks familiar already, right? This is the limit when x tends to 0, 1 over cosine to x, 2 sine x cosine x over x. This cosine comes here, the 2 comes here, and we have the limit of 2 cosine x over cosine of 2x sine x divided by x. Now, this is a terrible one. It's so terrible of a one that it's actually a 2. Now, this tends to 2 when x tends to 0. Who tells me why? Because I said so. Nope. Me saying it does not have to do with the fact that the cosine tends to 1. Okay, let's do a small apart here. Is this right? Correct. Exactly. So the limit of this quotient is 2. Now, who knows what the limit of this is? This is 1. So the limit is 2. No, you actually don't need L'Hopital's rule for this one. If I remember correctly, here, if you go to page 122 of your book, theorem 8, a very important trigonometric limit, it says limit when theta tends to 0 of sin of theta divided by theta is equal to 1. And the proof is a bit more creative than that Belgian guy's rule. So yeah, this limit is equal to 2. And you may be wondering, why do you show this to us if L'Hopital's rule is generally way easier? Because L'Hopital's rule doesn't always work. And you're going to find yourself in plenty of cases where you find a limit of a quotient of functions that tend to either 0 over 0 or infinity over infinity. Apply L'Hopital's rule, find yourself in the exact same position. So it's actually important that you know the properties of the things you're working with, because the easy, obvious tools are not always going to work, but the basics always work. Now, if we want to apply this rule, we have the limit when x tends to 0 of 2 times 1 plus tangent square of 2x over 1, right? This tends to 0, and so the limit is 2. It's easy when it works. It's really easy when it works. Now, I will suggest that you save L'Hopital's rule for cases that looks absolutely awful to treat with, which there exist. But it's generally more of a last resort than anything else. It's not guaranteed to work in all cases. Actually, if your function is not defined in somewhere around the point, somewhere around infinity or somewhere around 0, you're going to have all sorts of trouble, and you may even find wrong limits using L'Hopital's rule. So that's that. Actually, it's a pretty funny tool to have. And now you may have watched this old and not very well-known movie called The Lord of the Rings, and there one of the characters said, "But what about the second breakfast?" And we are going to do the exact same. What about the second derivative? Well, the second derivative, it's called this way, is the derivative of the derivative, literally. So the derivative is function, and in the case of elementary functions, which are the ones that we are working with most of the time, they're both continuous and differentiable. So we can derive them, and this is what we call the second derivative. We can also derive n times. We generally should be able to derive an infinite amount of times, but it's basically take the previous derivative and derive it. That's mostly it. Now, I'm going to delete this atrocity of nature, and let's see. 2.7.1. So our first exercise requires to find the second derivative of this. Actually, first, second, and third derivative of this. Okay, let's go. Now, composition of functions. Inner function, 3 minus 2x. Outer function, 7th power. The book said differentiation means continuity, but does it work the other way around? No, it doesn't. No, it doesn't. I can show you the following day. I can show you an example of a function that is continuous everywhere, but it's not differentiable in any point. Actually, one of my coworkers here in the department has the proof of that in his store. It's very, very fun person indeed. Now, all right, let's move on. So we have a composition of functions. First, inner function 3 minus 2x, outer function 7th power. So derivative of the composition, derivative of what's inside, times derivative of the outer function. With the argument that is inside. So this is minus 14, 3 minus 2x on power 6. We continue deriving. we have minus 14 multiplying derivative of what's inside times derivative of the outer function. Sorry, this is 6. And derivative number 3. Derivative number 3 is 168. I'm gonna put it this way. And so we go on it again. We have this thing right here. And then we have the derivative of this polynomial. Interestingly enough, this is minus 2 times 7, 6. This is, I'm going to show it to you here. Minus 2 squared times 7 times 6. And this is minus 2 cubed times 7 times 6 times 5. All right. This looks pretty regular, right? We have the minus 2 that always comes out. We have the 7. We go 1 degree less, multiply again, go 1 degree lower, and all that. This is a common strategy that is used to find nth derivatives of complicated functions. Generally, doing this kind of game with the coefficients helps you see the symmetry of it. Now, all right. All right. So from this one, we already know that this is 1 over cosine square of x. And this is cosine of x in power minus 2. So let's see what the second derivative says. We have a composition of functions. Inner function cosine of x, outer function power minus 2. So what we have here is the derivative of the inner function minus sine of x times derivative of this power minus 2. Yeah, cosine of x in power minus 3. Put this a bit. Sine of x, cosine of x in power minus 3. And you may be thinking, hey, maybe this has an even better form. Yes, it does. No, it doesn't. Sometimes things look one way, but then they're actually the opposite. And now, For the third derivative, the -2 stays. And we have a product of two functions. So this is derivative of the first times the second and derivative plus derivative of the second, which is minus sine of x times minus 3 cosine x in power minus 4 times sine of x. Now, this is derivative of what is inside. This is derivative of power minus 3, evaluated on cosine of x. Now, it's multiplied by that. The -2 is multiplying here. Everything is correct. So let's see where this leads us. This is cosine of x in power minus 2 plus this minus with this minus becomes a plus 3 sine square of x cosine of x in power minus 4. This looks pretty bad, right? It should be +2. No, my gentlemen, it should be +2. This is correct. So, I'm going to take this out. And this multiplies 1 plus 3 cosine x in power minus 4. If you take cosine in power minus 2 of x out here, this is equal to 4. So this is 8 over cosine squared of x. Minus 2, 3 sine squared divided by cosine fourth. Yep. Interesting turnout of events, I would say, when all this big trigonometric beast becomes 4. Now it's 11, so we're going to take a 10-minute break, and we will start again at 10 past. Like it literally means the world. Now let's do what we came here to do. Now, I'm going to show you an interesting and funny application of all these things. and that has to do with differentials. This equation right here reads differential of y with respect to x. Now, differential means a very small difference, and this is what you're going to be seeing in this first exercise. Good. So we have the function y equals 1 over x. And we are told x goes from 2 to 2.01. And what we want to calculate is this. We want to calculate this differential, this small difference. So now, instead of that d, which is actually a lowercase delta, delta is always used to represent differences or variation. The notation we're going to use is this. This means this is a variation that is not infinitely small. So this is kind of a measurable variation. So, as we know, this is, this is y of 2.01 minus y of 2. Okay, it's how the function changes when x changes. So we have x change in this way. And this is minus 0.01 over 4.02. And we're asked also, this is the approximate change. This is delta of y when x changes, and the new value of the function is this is all the mystery. Don't let very long instructions misguide you from the truth. The truth is these exercises are usually very simple, and the big problem you have to face is how to unphrase it, to say something. Interesting. Okay, there are many methods to add and subtract fractions, but the one I'm going to show you is the oldest one. Okay. If you have a sum or a difference of two fractions, this is defined as this one plus or minus this thing over here divided by this. So you probably never saw it this way, but this is how the sum or difference of two fractions is defined. So this is the lowest you can go. Now that we think about it, it's also extremely fast because you don't have to recalculate numerators or anything. You just go this times this minus this times this over this times this. This is 2, this is minus 2.01. So the difference is here. And here multiply both. Is this the easiest way to deal with fractions? Probably. Other methods may be useful in different situations, but as an abstract way to either add or subtract fractions, nothing beats this. I'm going to give you a little piece of insight here that you will probably carry with you for much time. Now, mathematics are a big house, a big castle with many layers and floors and different materials in the walls, and some wallpapers that are absolutely hideous. But well, it happens. But the essence behind all of it is that the foundation is well built. I mean, the foundations of mathematics are built to work always. So yeah, learn your definitions, learn your theorems, learn the fundamentals. And once you have the fundamentals, you can't lose. Now, the book recommends me to show you number 5. We have this function, and we know x changes 2%. It was 2%, right? Yeah. Okay. So the way we're going to do this is what economists quickly learn to forget about. They just do it. And so here we're going to let x0 be a point, our initial point. So notation of differentials, variation of y when x changes. We know this is y of x0 plus 2% minus y of x0, right? And this is equal to 1 over x0 times 1 plus 0.02 and all this squared minus 1 over x0 squared. All right. So I'm going to take common factor 1 over x0 squared. And what we have here is 1 divided by 1.02 squared minus 1. Now I have to do calculations. like this. And this is 1 over x0 squared. Someone who solves this calculation for me, please. Good. So what we have is that the function decreases approximately an 8%. All right, fair enough. So this function is decreasing. The y value decreases. Wait a second. Wait a second. There might be a mistake somewhere. Now, much better. This makes way more sense. So this variation is approximately minus 3.8%. And yeah, this will be it. This is the variation. And this is the differential notation that you will get sick and tired of reading. Okay, now we're going to move on, and I'm going to show you the really interesting stuff now. This is 2.8.5 and say okay. So how do we do this? Find tangent of 0 and pi over 2. We have a problem with that. Tangent of pi halves, this vertical line over here, gets infinitely large. However, there is something we can do. So which is the true question. Now, let's do more things. Let's, I don't know, derivate this. This is, I'm going to use the other notation, 1 plus tangent squared of x minus 1. This boy cancels this one out, so we have tangent squared of x, which is greater than 0 in all of our interval, right? Right. This means g is increasing. Monotonous, increasing, to be precise. Now, let's take a look at what we have here. What do we know about g? G of x is non-negative, increasing, now, the third thing I wrote there, is it true? Okay, I'm going to spoil this one for you. We actually don't need this. So, our function, namely tangent of x minus x, is non-negative. It's increasing, and it's only 0 in 1 point, and exactly 1 point. So what do we deduce from here? Non-negative, strictly increasing, starts in 0. So it goes up. Right or wrong? Right, thank you. So, are we finished? I would say we're finished. Now this means tangent of x minus x is greater than 0, which means tangent of x greater than x. Beautiful, huh? Yo. among all exercises that we have done in these 4 tutorials, I think this is the longest stretch we have made. So I will make sure that my video converter doesn't play me again, because I have spent 5 days trying to convert the videos from the other tutorials to an uploadable format and get it to you in MDH Play. So you might get a YouTube link for those later today. So take a good look at this, reflect on what we have done. We want to show this inequality. So we define a function that is equivalent to the inequality, and we try to prove that it's positive. We have that it's increasing, we have that it's starting 0, so it's always positive. Now, okay, we have 20 minutes left, so I'm going to show you number 8. Main application of derivatives is to calculate increasing intervals, decreasing intervals, and inflection points. And that's what we're going to do. So we have f of x equal to x cubed minus 12x plus 1. And we want to find increase intervals, decrease intervals, and inflection points. So let's see. First thing we do is derive it, because we want increase and decrease intervals. This is 3x squared minus 12. This is a small tool that will help us later. Now we derive this again for the inflection points, and we have six x for the second derivative. Now, for increase and decrease points. First of all, we know that the first derivative is continuous. So there are some things we're going to be able to do with that. First of all, we look for relative maximums and minimums. And we have two candidates, which can be either maximums, minimums, or critical points. But we will see about that. Now, okay, now, if x is smaller than minus 2, then the first derivative is positive, because this square is bigger than 4. And so function increases here. Between minus 2 and 2, x squared is smaller than 4, so the derivative is negative. So it decreases. And if x is larger than 2, the square primes over the 4. So Local maximum, x equal minus 2. Yeah, there we go. Local minimum, x equal 2. So we already kind of have an idea of what our curve does, right? It does something like this. It goes up, then down, goes from 0, continues down, and then in 2, it starts going again. Okay, so I'm going to erase this part so we can go on. With the other part. Concavity and convexity, and you know a function is convex if you trace its function and then you trace a straight line that crosses 2 points, and if that line is over the curve is convex, and if that line goes under the curve is concave. Easy, intuitive, instant, and extremely rigorous. Exactly how I like it. Now, convexity. So in order to see that, we have to analyze the second derivative. And the first thing we do is see what happens. Second derivative equals 0. This means x equals 0. So I have an inflection point at x equals 0. Now, for the sign, if x is smaller than 0, then this is more than 0 as well. So this part is concave. And if x is greater than 0, then f second of x is greater than 0. Good. So indeed, our inflection point is it's a point of change of concavity and convexity. Now, with all this, we are in a position where we can try and draw what the function possibly could be. So this is 0, this is minus 2, this is 2, this is minus 2. And in the end, there's one more thing that we should do, and that's find the zeros of this function. But I don't seem to find any here. They may be irrational. Yeah. So approximately here, the function does something like this. And then it goes up. That's more or less the function. I'm gonna redraw this small part here. Well, you got the idea. And this point here is approximately 0.5. So yeah, this is the complete analysis of a function. The exercise only asked us for increase and decrease intervals, but the applications of the second derivative makes the problem much more interesting. And now that you know how to do it, it's time to do it. Okay, there is here a very interesting one. Everybody look at problem 21. Okay. This is one of your typical exercises where the examiner wants to instill fear within your hearts, and with an statement that apparently contradicts the very foundations of what you are doing. So this is how we are going to solve it. Now, first of all, this is 3x squared, and this is 0 if and only if x equals 0. We look at our typical graph, and we see that if x is more than 0, this is positive. If x is greater than 0, this is positive as well. So our curve is something like this. Now, we have to show that although there is a point where the curve is flat, the function is actually increasing. So an all-time favorite, let epsilon greater than 0. We choose we choose 2 points. We are going to call them delta divided by 2 and minus delta divided by 2. Sorry. screw the two. This is two very small amounts, 2 points. Very close to 0, because that's what we want to check. The only problem we have is in 0. In all the rest of the points, positive derivative, the function is perfectly increasing. Now, our problem is 0. So we take 1 point that is above 0 and 1 point that is below 0. And let's see what happens. This is epsilon cube minus epsilon cube, right? This is epsilon cube minus epsilon cube. And this is 2 epsilon cube greater than 0. So the function is increasing. This is it, ladies and gentlemen. Now, as I tell you, please don't get scared by instructions. I mean, instructions are many times they are placed there to test your ability to abstract yourself from them. So in this case, show that fx equal x cube is increasing on the whole real line, even though f prime is not positive at every point. Looks scary. It's not. So you have to kind of backtrack on instructions. I want to see if I can find them, because I had a sheet with a selection of problems with very complicated instructions and details on how to read them. I will see if I find them. Otherwise, I will bring you more exercises that look scary. For example, you can check problem 28. What do we have to know for 10.1? You have to know everything for 10.1. When you get out of that exam and you ask your colleagues, hey, what did Ashraf and Herman ask? You will answer everything. What's up to notebook? Well, you can start on section P.1 and finish by the end of the book, basically. Let me see, what exactly do we have per lesson? Yeah. So you will get examine of chapters 1, 2, 3, and 4 in their entirety. Yeah, this was when the first time I took mathematical analysis. The teacher was kind of an interesting person, and the first time we asked him about, hey Oscar, what's going to be in the exam, he looked at us like this, and he said, well, everything. The exam was 6 questions, and we had a total of 6 hours to answer all of them. Only 2 persons in the class managed to answer the 6 problems in the 6 hours. And it was true. He said he would ask about everything, and goddamn, he did. We had, by the time, how many pages does this have? Yeah, a book more or less this thick. And yeah, we got asked about everything. Regardless, most of it builds from the immediately previous, so you shouldn't have a problem adapting to that. Now, it's who are presenting the assignment 2 exercises on Monday. Good question, Steven. Let's see. Are you able to present assignment 2? Okay. Martin, tell me your surname, please. Good. Okay, since you were the first person to offer yourself, you will present first and choose exercise. More. Jonathan Knudson. It's 2 S's, not 2 T's. And third person, Nikki Roani. So all you 3 will present the exercise on Monday, first thing before we begin. And bring your everything with you, because on next tutorial we're discussing implicit differentiation and antiderivatives, so things are going to get steamy probably. So come prepared, read your notes, read your lectures, listen to Ashraf, and you will be fine. Yeah, absolutely. But now it's lunchtime, guys. So thank you very much, you all, for joining. Remember to sleep well, drink water, don't skip meals unless you do so consciously, and stay safe.